At precisely 100,000 tons of displacement, moving a monolithic mass of high-yield steel across the ocean at sustained speeds exceeding 30 knots requires an incomprehensible output of continuous kinetic energy. This is not merely a ship. This is the USS Gerald R. Ford, designated CVN-78, a $13 billion maritime superstructure representing the absolute apex of modern naval engineering. To propel a structure equivalent in mass to a horizontal skyscraper, while simultaneously powering an internal grid that supports advanced electromagnetic launch systems, standard combustion engines are mathematically obsolete. The solution lies in mastering subatomic physics and extreme thermodynamics. The heart of the Gerald R. Ford does not burn oil, it splits atoms. For over 4 decades, the United States Navy relied on the Nimitz-class architecture, powered by the A4W nuclear reactors. While formidable, the A4W system was fundamentally limited by its reliance on mechanical steam distribution. The legacy reactors utilized massive networks of high-pressure steam piping to drive both propulsion turbines and the mechanical catapults used to launch aircraft. This decentralized steam system resulted in significant thermal energy loss, high maintenance overhead, and a rigid ceiling on electrical generation. As military aviation evolved, integrating directed energy weapons and advanced sensor arrays, the Nimitz-class grid simply lacked the megawatt capacity to sustain future operational loads. A total engineering paradigm shift was required. The mandate was clear: construct a power plant capable of generating a 250% increase in electrical capacity. Housed within the exact same dimensional footprint of the legacy reactor compartments, the engineering answer is the A1B reactor. Developed by Bechtel Marine Propulsion Corporation, the A1B standing for Aircraft Carrier, first generation, Bechtelus, a marvel of high-density energy packaging. The USS Gerald R. Ford houses 2 of these pressurized water reactors, or PWRs, operating in tandem deep within the heavily armored lower decks of the hull. Each individual A1B unit is engineered to deliver a thermal output of approximately 600 megawatts. Together, these twin cores generate a localized electrical distribution grid, operating at a staggering 13,800 volts. This is enough raw electrical power to sustain a mid-sized metropolitan city, constantly generated inside a moving steel vessel in the middle of the ocean. To understand the sheer complexity of this machine, we must examine the fuel core anatomy. The fission process begins within the reactor pressure vessel, a cylindrical containment structure forged from specialized high-yield carbon steel. Inside this vessel lies the reactor core, comprising precisely arranged fuel assemblies. Unlike commercial civilian reactors, the A1B utilizes highly enriched uranium, or E. This weapons-grade enrichment level is a critical engineering calculation. By utilizing HEU, the physical size of the reactor core can be drastically reduced, saving critical weight and volume inside the ship's hull. However, containing highly enriched uranium undergoing continuous fission presents an extreme material science challenge. The internal temperatures and neutron fluxes are severe enough to degrade standard industrial metals within hours. To counteract this, the uranium fuel rods are encased in a highly specialized zirconium alloy cladding. Zirconium is selected for its extremely low neutron absorption cross-section. This means it allows the neutrons necessary for the fission chain reaction to pass through freely, while providing an impenetrable physical barrier against the intensely radioactive fission byproducts. The cladding must withstand constant thermal expansion and contraction, resisting rapid oxidation and structural fatigue over a projected lifespan of 50 years. With the fission reaction localized and controlled by neutron-absorbing control rods, the generation of extreme thermal energy begins. The A1B operates on a dual-loop thermodynamic cycle. In the primary coolant loop, chemically purified water is pumped directly through the nuclear core. As it flows past the superheated zirconium-clad fuel rods, the water absorbs massive amounts of thermal energy. To prevent this water from boiling into steam inside the reactor core, which would cause a catastrophic loss of cooling efficiency and potential core meltdown, the primary loop is pressurized to over 2,000 pounds per square inch. Under this immense pressure, the primary coolant remains in a liquid state even as its temperature exceeds 300 degrees Celsius. This superheated, highly pressurized, and radioactive water is then circulated into a massive heat exchanger, known as the steam generator. Here, the primary coolant flows through thousands of micro-machine tubes constructed from Inconel, an austenitic nickel-chromium-based superalloy specifically designed for extreme pressure and corrosion resistance. The heat from the primary tubes is transferred through the metallic walls to a completely separate secondary water loop. Because the secondary loop operates at a lower pressure, the transferred heat instantly flashes the secondary water into high-pressure, non-radioactive steam. This pristine high-velocity steam is the final kinetic transfer medium. It is channeled through heavily insulated piping systems to drive the massive multi-stage propulsion turbines connected to the 4 propeller shafts, pushing the 100,000-ton Leviathan through the water. Simultaneously, the steam rotates high-capacity electrical turbine generators, converting mechanical rotation into the 13,800-volt electrical grid that breathes life into every circuit, sensor, and electromagnetic system on the USS Gerald R. Ford. The precision required to maintain this thermodynamic equilibrium is absolute. A variance in pressure, a microscopic flaw in the Inconel tubing, or a minor drop in coolant flow would trigger automated shutdown sequences, crippling the vessel. Constructing a nuclear power plant designed to operate inside a constantly moving, combat-capable steel vessel demands an entirely different paradigm of manufacturing. The assembly of the A1B Twin Nuclear Cores at Huntington Ingalls Industries' Newport News shipbuilding facility in Virginia is a masterclass in heavy industrial fabrication intersecting with microscopic precision. This process begins long before the hull takes shape, deep within specialized manufacturing sectors operating under stringent cleanroom environments. The internal components of the reactor core, particularly the fuel assemblies and the control rod drive mechanisms, cannot be exposed to standard atmospheric conditions. Even microscopic particulate matter, organic contaminants, or trace chemical residues can induce catastrophic localized corrosion when subjected to the extreme radiation and thermal stresses of an active fission cycle. Consequently, the assembly of the primary core internals is conducted within industrial cleanroom facilities meeting strict Class 1000 standards. Here, the ambient air is continuously filtered to maintain fewer than 1,000 particles, greater than half a micron per cubic foot. Technicians clad in full-body sterile suits assemble the complex lattice of zirconium-clad fuel rods with methodical precision. Every hand tool is meticulously accounted for. Every surface is rigorously sterilized. The introduction of foreign material at this stage is an unacceptable engineering failure. Surrounding this delicate, highly reactive core is the primary containment barrier, the reactor pressure vessel, or RPV. This is not fabricated from standard maritime steel. The RPV is forged from advanced alloys, predominantly utilizing variants of HY100 steel, a high-yield carbon alloy engineered to withstand stress loads exceeding 100,000 pounds per square inch. The fabrication of the RPV cannot rely on simple casting methods, which often leave microscopic voids or structural weaknesses within the metal matrix. Instead, massive monolithic ingots of high-grade steel are heated to their plastic state and subjected to immense compressive forces using heavy hydraulic forging presses. These presses, capable of exerting tens of thousands of tons of force, literally crush the steel into shape, aligning its crystalline grain structure to maximize tensile strength and fracture toughness. The resulting vessel walls, measuring several inches thick, form an impenetrable fortress designed to contain extreme hydrostatic pressure and relentless neutron bombardment for half a century without succumbing to metal fatigue. Once the primary forgings are completed, the integration of the reactor modules requires welding techniques that push the boundaries of mechanical engineering. The intricate network of primary coolant piping, heat exchangers, and the main pressure vessel must be joined seamlessly. Traditional manual welding is insufficient for this task. The construction relies heavily on automated orbital welding technology. Specialized robotic welding arms, programmed with sub-millimeter precision, revolve around the circumference of the heavy steel pipes. These machines lay down multiple passes of weld metal, perfectly controlling the heat input, travel speed, and shielding gas flow to create a metallurgical bond that is structurally identical to the base metal itself. Before the robotic welders even strike an arc, the massive steel components undergo rigorous preheating via heavy induction coils to prevent thermal shock and hydrogen-induced cracking. Following the weld, a slow, highly controlled post-weld heat treatment process relieves residual internal stresses that have accumulated within the steel matrix. The clearance tolerances maintained during these mechanical assemblies are microscopic, frequently engineered down to 1/1000th of an inch, or 0.001 inches. Such extreme precision is an absolute necessity. At operating temperatures exceeding 300 degrees Celsius and internal pressures surpassing 2000 psi, any dimensional discrepancy, thermal expansion mismatch, or weld porosity will result in highly radioactive superheated water breaching the primary containment loop. The culmination of this manufacturing process is the physical integration of the completed A1B reactor compartments into the skeletal framework of the USS Gerald R. Ford. This operation takes place within the cavernous expanse of Dry Dock 12. The reactor modules, now fully encased in massive lead and steel biological shielding designed to protect the crew from ionizing radiation, weigh hundreds of tons. Moving these colossal units requires one of the most powerful lifting mechanisms on the planet, the massive 1,050-ton capacity gantry crane spanning the dry dock, known industrially as Big Blue. Big Blue slowly hoists the pre-packaged nuclear reactor module from the assembly staging area. The process of lowering the module deep into the subterranean levels of the carrier's hull is a nerve-wracking display of spatial logistics. Riggers and structural engineers carefully guide the massive steel structure through a labyrinth of bulkheads, navigating clearances that sometimes measure only a few inches. The integration is not merely dropping a box into a slot. The module must be seated perfectly onto specially engineered shock-absorbing mounts. This mounting system utilizes immense elastomeric bearings and hydraulic dampers capable of dissipating massive amounts of kinetic energy. This ensures that even if the carrier's hull violently flexes during heavy seas or explosive shockwaves, the reactor core remains perfectly aligned and geometrically stable. Once seated and mechanically locked into the keel, miles of heavy-gauge cabling and secondary heat exchangers are hermetically sealed, transforming the A1B reactor into the beating heart of the world's most advanced warship. Before the nuclear fuel is ever allowed to reach criticality, the entire A1B propulsion and containment architecture must undergo a brutal gauntlet of quality control and extreme stress simulations. The physical limits of the constructed systems are deliberately pushed far beyond their maximum operational parameters. The primary coolant loop, designed to operate at over 2,000 pounds per square inch, Engineers pump chemically pure water into the sealed reactor piping and artificially raise the internal pressure to 150% of its maximum rated capacity exceeding 3,000 psi. This pressure is held constant for extended durations, while acoustic emission sensors and highly sensitive strain gauges monitor the HY100 steel pressure vessel and its connecting in-canal pipework. They measure the elastic deformation of the metal, ensuring it does not cross into plastic, irreversible deformation. A failure here, even a microscopic drop in pressure, dictates the immediate rejection and complete refabrication of the compromised module. However, hydrostatic pressure alone cannot verify the internal integrity of the metallurgical bonds. Therefore, Huntington Ingalls Industries mandates exhaustive non-destructive evaluation, or NDE, protocols. Every single structural and pressure-retaining weld within the reactor compartment undergoes 100% radiographic inspection. Utilizing high-energy X-ray and gamma-ray radiography, technicians peer directly through inches of solid high-yield steel to capture the internal atomic structure of the weld joints on specialized industrial film. They are actively searching for microfractures, slag inclusions, or internal porosity gas bubbles trapped within the metal matrix during the welding process. Even a void measuring a fraction of a millimeter can act as a stress concentrator, propagating into a catastrophic shear fracture under the relentless thermal cycling of a 50-year operational lifespan. Furthermore, automated ultrasonic phased array scanners are deployed to detect internal delamination within the steel plates themselves. This is followed by the installation of the biological shielding heavy layers of lead plate, high-density concrete, and borated polyethylene designed to absorb stray neutron flux. Only when the atomic structure of the entire containment system is proven completely flawless is the reactor certified for fueling. When the twin A1B reactors finally achieve criticality, the immediate impact on the operational capability of the USS Gerald R. Ford is unprecedented in naval history. The combined thermal output of the two cores translates into an electrical generation capacity that dwarfs the legacy Nimitz class by 250%, operating a 13,800-volt internal distribution grid through a series of advanced solid-state power conversion systems. The A1B effectively powers a self-contained, mid-size industrial city that floats. Yet the most profound engineering achievement lies in its endurance. Thanks to the highly enriched uranium fuel rods and the advanced thermodynamic efficiency of the core design, the A1B reactors possess a 50-year operational lifespan without ever requiring a refueling procedure. Unlike previous generations of aircraft carriers, which require a multi-year, multi-billion-dollar refueling and complex overhaul at the midpoint of their service life, the Ford class is designed to operate continuously for half a century. This permanently eliminates the most complex maritime logistical vulnerability in the United States Navy's arsenal. This limitless, high-density electrical grid fundamentally redefines the parameters of maritime mechanical engineering. The massive power output of the A1B is the critical enabler that allows the USS Gerald R. Ford to completely abandon the heavy maintenance-intensive mechanical steam systems of the past. The legacy steam catapults have been replaced by the Electromagnetic Aircraft Launch System, or EMLS. EMLS utilizes massive linear induction motors, requiring instantaneous surges of megawatts to propel a 30-ton fighter jet to 160 miles per hour in under 3 seconds. To prevent grid brownouts during a launch, the A1B feeds massive kinetic energy storage groups heavy flywheel alternators that spin at high speeds, storing rotational energy and discharging it in rapid, 2-second bursts. Simultaneously, the legacy hydraulic arresting cables have been replaced by the Advanced Arresting Gear, or AAG, which utilizes water twisters and massive electric motors to absorb the kinetic energy of landing aircraft. Neither of these revolutionary systems could function without the sheer, uncompromising electrical output generated by the twin nuclear cores. Ultimately, the construction of the A1B reactor system is not merely an achievement in shipbuilding. It is a triumph of applied physics and heavy industrial manufacturing. It represents the absolute mastery of material science, extreme thermodynamics, and subatomic mechanics, By confining the power of a star within a forged steel vessel, engineering the ultimate heat transfer mechanisms, and ensuring absolute metallurgical perfection, the United States has not just built an aircraft carrier, they have constructed the most complex, energy-dense, and enduring mobile machine ever conceived by human engineering.